All right, let's dive right into this explainer and tackle an invisible threat that is literally eating away at your facility's power quality: harmonic distortion. Look, if you're managing a modern facility, nonlinear loads are everywhere, and they are silently wreaking havoc on your electrical systems. So today, we're breaking down exactly how to protect your equipment with the ultimate harmonic filter selection guide. Before we even try to solve the problem, we absolutely have to understand the benchmark we're striving for, and that is the IEEE 519 standard. It's the definitive guideline for keeping those chaotic harmonics in check. When you introduce variable frequency drives, VFDs, and other nonlinear loads into your environment, they create massive electrical turbulence. Complying with IEEE 519 is not just about ticking some compliance box, it's about ensuring the fundamental health and survival of your entire operation. So here is our roadmap. We're going to start by laying out the power quality problem, then we'll jump into our 3 hardware contenders: passive filters, active filters, and compound filters. And we'll wrap the whole thing up with an ultimate selection checklist so you can find the fit that's just right for your specific site. Okay, Section 1, the power quality problem, the invisible threat. The reality is pretty simple. If you have VFDs operating out on your floor, you are inherently generating harmonics. These aren't just minor little inefficiencies. They significantly degrade your power quality. Left unchecked, these nonlinear loads risk severe equipment damage, nasty unplanned downtime, and, of course, falling out of compliance with standards like IEEE 519. It's a serious problem, and it requires targeted, deliberate mitigation. Moving into Section 2, passive filters, or what I like to call rugged reliability. Meet contender number 1. These passive filters operate using your classic simple LC circuits, so inductance and capacitance. Because of that traditional design, they are entirely fixed and static. They're specifically tuned to instantly tackle certain low-order frequencies, particularly the 5th or 7th order harmonics. The response time is instantaneous, which is great, but remember, it's an instantaneous response only to the specific frequencies it was engineered to target. It doesn't adapt. Like any good workhorse, it's got distinct strengths and weaknesses. On the plus side, you're looking at a much lower initial investment. It's incredibly durable and boasts a lifespan of 15 to over 30 years, which is just fantastic. But it has some critical flaws. It takes up a massive physical footprint, sometimes we're talking the size of a large refrigerator, and it is terrible at handling changing loads. Plus, it carries a high risk of system resonance and can actually cause a leading power factor when you're operating at light loads.
So where does this rugged reliability actually belong? Well, imagine a massive, steady HVAC system, or a single-drive application running constant pumps or fans. That's the perfect environment. It absolutely thrives in situations where the load is constant, totally predictable, and where you just need a durable set-it-and-forget-it solution.
All right, Section 3, active filters, dynamic precision. If the passive filter is the rugged workhorse, this guy is the agile brain of the operation. This is a massive leap in technology. Instead of relying on those static LC circuits, the active filter uses highly sophisticated power electronics. We're talking IGBTs, which act as super-fast digital switches. It literally reads the line and injects counter harmonics in real time to cancel out the distortion on the fly. And that gives the active filter some literal superpowers. It acts like a high-tech scalpel. Because it's fully dynamic, it adapts instantly to load changes with a blazing fast response time of under 1 to 2 milliseconds. Plus, it's not limited to just the 5th or 7th order. It provides wide spectrum filtering all the way up to the 50th order. And perhaps best of all, there is absolutely zero to very low risk of system resonance. You also get dynamic power factor correction without those leading power factor issues, all packed into a highly compact size. But hey, precision comes at a price, right? The trade-off for all that dynamic correction and compact sizing is a notably higher upfront cost. It requires more sophisticated maintenance, too. And because it's actively using power electronics, the unit itself consumes power to operate, usually about 1 to 3% of your total load power. Picture a data center, a modern factory production line, or a hospital. These are intensely dynamic environments with multiple, constantly shifting variable loads. That is exactly where you need the lightning-fast precision and real-time correction of an active filter. It effortlessly balances the load and manages a highly unpredictable electrical landscape. Moving on to Section 4, compound filters, the heavyweight hybrids. This is our third contender, stepping in when the environment is so demanding that neither of the first two alone will cut it. The crucial takeaway here is that this heavyweight champion literally gives you the best of both worlds. It utilizes passive components for the cost-effective bulk filtering of those heavy, low-order harmonics. But then, at the exact same time, it uses active components for the high-speed, precise mitigation of unpredictable, higher-order harmonics.
When you merge these technologies, the specs are incredibly impressive. You get dynamic power factor correction, incredibly broad spectrum coverage, and a very low resonance risk. But merging static and dynamic systems means highly complex engineering. Because of this heavy-duty dual architecture, it absolutely comes with the highest initial cost of the three options by far.
Look, you aren't going to throw a compound filter on a standard HVAC system. But if you're running an extremely high-power, complex industrial site, think a massive steel mill or a sprawling mining operation, this is your ultimate solution. Those sites have heavy, steady baseload harmonics mixed with violent, fluctuating harmonic loads. Only a hybrid system is tough enough and smart enough to tackle that kind of extreme environment. And that brings us to Section 5, your ultimate selection checklist. Let's pull all these technical specs together into some actionable advice for your facility.
Comparing these options maps out our Goldilocks scenario perfectly. You've got the ruggedness of the passive, the agility of the active, and the sheer brute capability of the compound filter. Think about how adaptability scales from totally fixed to fully dynamic, while your resonance risk drops from high down to near zero. But you also have to weigh that initial cost scaling up to the highest bracket. And finally, lifespan. The passive filter definitely wins the longevity race at 15 to 30 years, while the active filter will generally need replacement around that 10 to 15-year mark.
Making your choice really just comes down to 3 steps. Step 1, assess your load stability. Is your load single and constant, or is it wildly variable? Step 2, evaluate your environment and power scale. Are you managing dynamic sources like a data center, or do you have extreme high-magnitude power needs like a steel mill? And step 3, check your budget and space constraints. The passive filter might save you money, but do you have the literal floor space for its massive footprint? The active is compact and high performance, but can you get approval for that higher upfront cost? Take a really hard look at your facility's variable frequency drives and nonlinear loads today. Don't wait for your equipment to fail or for those massive compliance fines to hit. Ask yourself, does your specific load profile demand the rugged workhorse, the agile brain, or the heavyweight champion? Finding the exact right fit is absolutely key to mastering your power quality. Until next time, keep analyzing, keep optimizing, and stay focused on the facts.